Hello everyone. Good evening. Welcome to my channel Civil Concepts. Today we are going to learn about the calculation of the mixed design. Today we will see the calculation for the 50 grade of concrete, that is M50 by 20, where 20 is the nominal size of the aggregate. We will follow the IS code, that is 10262 2019. So starting from the beginning, we can see here the Excel sheet. Here I will explain each and every steps, and finally I will upload this Excel sheet in the description box also. So this one is the overview of the Excel sheet. So now we are going to start. Let's see. Here the grade of concrete is M50, and for the M50 grade of concrete, the characteristics compressive strength is 50 megapascal, and the for the target compressive strength, which is that is at the 28 days, we have followed the Nepal specifications, that is as per standard specification for roads and bridge, table 20.3b. Here I will show you the code book. Yeah, here we can see the concrete class and strength for bridge, flyover and underpass. Here the M50 grade of concrete, which I'm going to explain, is used for the bridges. So here we can see the for the M50 by 20 grade of concrete, here we can see the target strength is 61 megapascal. So from this table we have taken this one 61, and the maximum size of the aggregate we have used is 20 mm, and the slump we have used is 200 plus minus 20 mm, and the degree of quality control is good, and the type of exposure for the Nepal weather condition, it's severe. So for the here we can see the specification IS 456 2000 table 3. Yeah, here I will show the table 3. Yeah, here we can see the table 3 for the site condition where we are for which we are designing. Here is the concrete surface exposed to severe rain, alternate wetting and drying, or occasional freezing whilst wet or severe condensation. So the environmental condition with adapting we are adapting here is severe. So here we have taken the severe, and for the severe exposure condition, the minimum cement content we can see in the table 5. Here I have taken the snapshot of the table. Yeah, here we can see for the severe exposure condition, for the RCC concrete, the minimum cement content for the severe is 320 kg, and the maximum water cement ratio is 0.45. So from this table we have taken this 320 and 0.45. The type of mixing, the concrete we are producing is from the batching plant, so I have written here is the batching plant. Yeah, here we can see the constituents that we are using in the concrete, that is the cement, mineral admixture, means the fly ash, and the admixture, this is the chemical admixture, and here is the 20 mm aggregate, 10 mm aggregate, sand. Yeah, we can see for the cement, the brand we are using is OPC 53 grade, brand is sebum, and the specific gravity that we have found out in the lab was 3.14, and the mineral admixture, that is the fly ash, we are using is the Hind Super FA, whose specific gravity we have calculated in the lab was 2.11, and the chemical admixture we are using is the SBT, that is this is the Chinese admixture, and specific gravity which we have found out was 1.08, and here is the 20 aggregate, 10 aggregate specific gravity value, and the water absorption values that this all we have calculated in the lab. Here we can see the sand, which is specific gravity is 2.664 and water absorption is 1.03. The mixed design that we have done here is in the SSD condition, that is saturated surface dry condition. So if the or aggregate and sand is in saturated surface dry condition, then the surface moisture will be 0 0. Yeah, and now in the third step we will calculate the water cement ratio. For the exposure condition severe, maximum water cement ratio that we have taken from the IS 456 is 0.45, and based on the our practical experience, we have done so many of trials in the lab, we had adopted water cement ratio as 0.349. It will change as per the exposure condition and the site distance from the batching plant. So it's practically depends upon the experience. So from my experience I have taken the water cement ratio this much. Now we will go to the fourth step. Here we will go for the selection of water content. So for the selection of water content, we will see in the table 4 of IS 10262. Yeah, I will show you the IS 10262 table 4. This is table 5. Yeah, table 4. The maximum size of aggregate that we are using for this mix design is 20 so for 20 the water content is 186 kg, so 186 liter, but this much water is for the 25 to 50 slump value. Here we can see, yeah, here for the desired workability other than 50 slump, the required water content may be increased or decreased by about 3% for each increase or decrease of 25 slump, or may be established by trial. So this much is for the 25 to 50 slump, but the slump requirement for our site is 180 to 220 that is 200 plus minus 20. So taking the 200 slump, if we take the 200 slump, so as per IS 10262, we have to increase 3% water for every additional 25 slump. So for the 50 slump, the water was 186 liter, but for the 200 slump, we have calculated here 186 plus 200 minus 50, that is this 200 minus 50 divided 25 into 0.03, this one is the 3% into 186. Here the slump value is 200, so the water content will obviously be more, so we have calculated added here, and which we have achieved is 219.48 kg. This much is for the 200 slump, and for the high grade concrete, normally we have to use the admixture to control the slump. Since our batching plant is almost 30 to 40 minutes away from the site, so if we don't use the super plasticizer, then the concrete will start setting. So we have used the admixture, which is the water reducing admixture. So if we use the admixture, water reducing admixture, then water content can be reduced by 30% or above. So for this I will show you the as per the clause 6.1.4 of the 10262 IS code, clause 6.1.4. Here we can see 6.1.4. 6.1.4. Here in this clause we can clearly see high strength concrete mixes usually have a low water cementitious material ratio. These low water cementitious ratios are generally only attributable with high range water reducing admixture. PCE type superplasticizer which reduce water content by 30% or above at appropriate dosage may be used. Here we can clearly see that if we use the high range admixture, then we can reduce the water content by 30% or above. Here we have since we have done so many of trials in our lab, so from that we have achieved that we can reduce the water content by up to 32%. So we have to reduce this much of water, 32%. So reducing the 32% of water, 219.48 into 100 minus 32% is 68%, so 0.68. So if we multiply this two value, we will achieve this one. Now moving to the fifth step. Here the required cement. Since we have earlier calculated the water cement ratio is 0.349 based on the experience, and the water content we have achieved was 149.25. So if we divide by water cement ratio, we will get the required cement. Here we have used the fly ash. So if we use the fly ash, we have to increase the cementitious material content. That is, cementitious material content means cement plus fly ash. The summation of both can be increased by 11%, which we can see from the clause 5.4.1 of the IS 10262 code. Here I will show you clause 5.4.1. 5.4.1. 5.4.1. Yeah, here we can see the decision on increase in cementitious material content and its percentage may be based on experience and trials, or the cementitious material content so calculated may be increased by 10% for preliminary trial. So from this we have increased the cementitious content by 10%. Here it's have maybe increased by 10% for preliminary trial. And here also we can see in certain situation, while using part replacement of cement by fly ash, GGBS, silica fume and other mineral admixture, increase in cementitious material content may be particularly flies 20% or more also. And here we can see the 10%. Minimum is 10%. We can go above that also. This is purely depends upon the trial. If we can replace cement with fly ash by 20% or 30%, then it will be cost efficient. But from the trial, the fly ash that we are using in our lab, here we can increase the cementitious material content by 11% only. It depends upon the brand of the fly ash also. So we have increased here. So we have multiplied 1.11 into cement content. We have achieved the cementitious material content. Now the fly ash we have the cement we have replaced with the fly ash is with the 10%. So calculating the 10% of the total cementitious material content, we will achieve 47.469. Now cement, if we subtract the cementitious material content with fly ash, we will achieve the amount of cement. The free water cement ratio, this one we have earlier calculated 0.349, it's the same. And the water, It's also the same that we have earlier calculated, 149.25. And the admixture, that is chemical admixture, water reducing admixture. Here we have used 1.22%. Uh, Actually, we have reduced 0.5% also during the trial time, but the concrete that we have obtained was not so much of good quality. So based on several trials, we have finalized this much percentage of the water reducing admixture being used in our concrete. So if we calculate 1.22% of cementitious material, that is 474.692, we will achieve 5.791 kg. Now this one is the water cementitious ratio. This one is different from water cement ratio. Since in this M50 grade concrete we have used the fly ash, so cement and fly ash together is called the cementitious material. So here we have to take the water cementitious ratio, not the water cement ratio. If we have used only cement, then we have to calculate the water cement ratio. But if we use any other mineral admixture, that is fly ash, microsilica or GGBS, then we have to calculate the water cementitious ratio. For this we have divided the water, that is 149.25, by cementitious material content, that is 474.692. Moving to the next step, that is step number 6. Here we will calculate the fine aggregate and coarse aggregate. So the fine aggregate, that is sand, which we are using on our site, is from the zone 2. For this I will show you the IS table, IS 383 2016. Here we have see the classification of the zone classification of the sand, and this is the sieve number. IS sieve 10 mm, 4.75, 2.36, 1.18, 600 micron, 300 micron, 150 micron. I will show you the sieve analysis test data sheet that we have taken in our lab. Yeah, here I will show you the sieve analysis data record for the sand. The percentage passing is here. This lies in this envelope. Here we can see the specification. 100 in 10 mm sieve size, the 100 mm passing minimum is 100 mm passing and maximum is also 100 mm passing. And in the 4.75 mm, 90 mm 90 percentage minimum passing and maximum 100. Here we can see the specification. This specification clearly matches with the zone 2. Here we can see 100, 100, 90, 90, 75, 100, 55, 90, 35, 59, 8, 30, 0, 10. Here we can see this specification matches with the zone 2. In 10 mm 100, 90, 100, 75, 100, 55, 90, 35, 59, 8, 30, 0, 10. So from this we have taken this one, zone 2. So for the zone 2 fine aggregate, the coarse aggregate ratio is 0.62 for the water cement ratio of 0.5. Here we can see this one in the clause table 5, clause 5.6 of 10262. Table 5, I will show you the table 5, table 4, table 5. Yeah, here they have clearly mentioned that for table 5, volume of coarse aggregate per unit volume of total aggregate for different zones of fine aggregate for water cement or water cementitious material ratio of 0.5. The nominal maximum size of aggregate we are using is 20 mm, and the sand zone classification is zone 2. So for the zone 2 and 20 mm maximum size of aggregate, the ratio is 0.62. From here we have taken this ratio 0.62. For the water cement ratio or water cement ratio 0.5, the aggregate ratio is 0.62, but in our case the water cementitious ratio that we have calculated in the previous step here is 0.314. So for the water cement ratio 314, the coarse aggregate ratio we have to calculate. So for the calculation I will take you to the clause 5.5.1. 5.5.1. 5.5.1. Yeah, here I will show you. Approximate values for this aggregate volume are given in table 5 for a water cement or water cement ratio of 0.5, which may be suitably adjusted for other ratios. The proportion of volume of coarse aggregate to that of total aggregate is increased at the rate of 0.01 for every increase in water cement or cementitious material ratio by 0.05 and decreased at the rate of 0.01 for every increase in water cement ratio by 0.05. The statement that they have written is little bit confusing, so I will explain you clearly. Here we can see for the 0.5 water cement ratio, the coarse the coarse aggregate by total aggregate ratio is 0.62, but in our case the water cementitious ratio is 0.314, means the water cementitious ratio is decreased from the 0.5 to 0.314. If water cement ratio gets decreased, the coarse aggregate ratio will be increased. So for that only we have added this one 0.62 plus 0.5 by how much it's decreasing, that much we have to increase the aggregate ratio. So the initial water cement ratio was 0.5, so from there it's 0.5 minus 0.314, which is the present water cementitious ratio, divided 0.05 into 0.01. Here they have clearly mentioned na, for at the rate of 0.01 for every increase in water cement ratio by 0.05. So we have to calculate by how much the water cement ratio is increasing. So for that we have divided with 0.05 and multiplied with 0.01. So after calculating this we will be get 0.6572. And one more thing, for the pumpable concrete, the concrete that we are using in our site is pumpable concrete. We have to pump it through the pump. So for the pumpable concrete, coarse aggregate can be reduced up to 10%, which they have mentioned in the IS 10262 clause 5.5.2. Clause 5.5.2. Yeah, here they have mentioned. For more workable concrete mixes, which is sometimes required when placement is by pump or when the concrete is required to be worked around congested reinforcing steel, it may be desirable to reduce the estimated coarse aggregate content determined using table 5 up to 10%. Up to means the maximum is we can reduce is up to 10%. Up to 10% we can decrease. So we have decreased this ratio, that is 0.6572. So here we can see we have reduced this one 0.6572 minus 10% of 0.6572, will be getting 0.59. Here we can see the final proportion of coarse aggregate that we have achieved is 0.59. Now there are two types of aggregate that we are using in our site. That is, one is the 20 mm down and other is the 10 mm down. So it's a little a confusing thing. I will explain you clearly. You may be thinking that how much percentage of 20 mm aggregate we have to use and how much 10 mm down aggregate we have to use. So this all depends upon the trial. We have done the aggregate sieve analysis test in the lab. I will show you. Here we can see the sieve analysis test result of the aggregate. Here initially we have used the 60% of 20 down aggregate and 40% of 10 down aggregate. While taking that ratio, we have not achieved the passing percentage is for the specification. So we go on changing and changing. First, initially we have used 60/40. Again, in the next, we have used 65/35, and finally we have used 70/30. And when we take 70% of 20 down aggregate and 30% of 10 down aggregate, the sieve analysis value get come inside the envelope. So this one varies from the site to site because the size of the aggregate varies from place to place. This is for the site that I am working, so it may be different for your site condition. So from that we have calculated that 70% of 20 down aggregate I have used, and 30% of 10 down aggregate I have used. So multiplying the 70% with 0.59, we will get 0.41, and multiplying the 30% with 0.59, we will get 0.18. And the final proportion of fine aggregate, that is sand. So for this we have to subtract 100% minus this one aggregate percentage, that is 59%. So we will get 0.41, that is 41%. Now as per the IS 10262 2019, we are calculating the mix design for the 1 cubic meter concrete. So for now we will calculate the volume and then the mass of the each and every constituents of the concrete, that is cement, fly ash, water, admixture, each and everything. So first we will calculate the volume of cement. So the we all know that is the formula for density equals mass by volume. Density equal to mass by volume. So if we take the volume part up, then the volume part equals mass by density. So it's the same, mass by density into 1 by 1000. We have multiplied for converting the unit conversion for that one only, nothing much more. So mass of the cement we have calculated earlier. I will show you mass of the cement here. It's the 427.223. From there I have taken mass of the sand, specific gravity of cement. Here earlier I have shown you the specific gravity value here, 3.14, that we have calculated in the lab itself. We can calculate this one in the lab. Later in the next video I will show you how to calculate the specific gravity of cement, aggregate, sand also. But as of now I will show you the calculation sheet. So if we divide the mass by specific gravity into 1 by 1000, we will be getting 0.136. Same is the case with volume of fly ash. We will divide mass by density. Density and specific gravity is almost same. So if we multiply mass of the fly ash, here we can see it's 47.469 kg, and the specific gravity of fly ash, that is mineral admixture. Mineral admixture, it's same the fly ash, it's 2.11. So if we divide mass by density, we will be getting 0.022 cubic meter. Similar is the case with the volume of water, mass of water that we have calculated, divided with the specific gravity of water. Specific gravity of water is 1. So if we divide this, we will be getting 0.149. Now we will calculate the volume of admixture, that is water reducing admixture that we have used. Here also we will divide mass by specific gravity. I will show you the mass of admixture. Mass of admixture is 5.791, and the specific gravity of admixture is 1.08. If we divide that value, we will get 0.005362. And the volume of entrapped air, that we can see 1% of total volume of concrete. This we will see from the table 3 clause 5.2. 5.2, 5.2, yeah, here. The maximum size of aggregate we are using 20. So for the 20, entrapped air percentage is 1. So from here, I have taken 1%. Now the volume of all in aggregate means we have calculated the volume of cement, fly ash, water, admixture, and entrapped air. But in the concrete, there is aggregate part also, that is fine aggregate and coarse aggregate. So that we will calculate. Since we have taken the total volume as 1, so subtracting the volume of cement, fly ash, water, admixture, and entrapped air from the 1, will get 0.6776 cubic meter. Now we have calculated the volume. Now we will calculate the mass. So for calculating the mass of coarse aggregate, that is 20 for the 20 down aggregate, here we have, you can see the formula: volume of all in aggregate into volume of 20 down aggregate into specific gravity of 20 down aggregate into 1000. This all formula I am using is from the IS code only. I will show you. It's all from the IS 10262. Here I will show you. There is example they have taken for the clarification of this code. They have shown some of the examples. From here only I have taken the, here we can see this the volume of cement. Here we can see the formula: volume of water, volume of admixture, volume of all in aggregate. The all formula we have used from this code only. Yeah, for this mass of coarse aggregate we are seeing equal to G. What is G? Here we can see G, volume of all in aggregate, volume of all in aggregate into volume of coarse aggregate into specific gravity coarse aggregate into 1000. From here only we have taken the formula. So if you multiply volume of all in aggregate, which is 0.6776, into volume of 20 aggregate, volume of 20 aggregate, I will show you. Volume of 20 aggregate is 0.41 and 0.41 into specific gravity of 20 aggregate, that we can see here. The 20 aggregate is specific gravity value is 2.613. So if we multiply all these value, we will get the coarse aggregate value is 725.933 kg. Similar is the case with mass of coarse aggregate, 10 down aggregate. Same is the formula. We can see the same formula: volume of all in aggregate, that is 0.6776 into volume of 10 aggregate. Volume of 10 aggregate that we have calculated earlier is 0.18 into specific gravity of 10 aggregate, and multiplying that all value with 1000 will get this much. Same is with the mass of sand. So for the volume of all in aggregate, it's the same: 0.6776 into volume of fine aggregate. Volume of fine aggregate here we have earlier calculated, which was 0.41, and into specific gravity of fine aggregate. Here we can see the specific gravity of fine aggregate here, which is 2.664. Yeah, into 1000. If you multiply all these, we will get this much. Now I have made the table. The grade of concrete that we have calculated is M50 by 20, where the water cementitious ratio, where I have earlier explained about the water cement ratio, when to take water cement ratio and when to take water cementitious ratio. So water cement ratio is 0.314, and the cementitious content, that is cement plus fly ash, is 475. Here we can see, from here only I have taken cementitious material content 474.692. If we round off this value, we'll get 475, 475. Yeah, here I have shown you the cement, fly ash, water, 20 aggregate, 10 aggregate, sand, admixture content. This all mixed design we have done in the SSD condition, saturated surface dry condition. So I have summarized that calculated value only. This cement I have taken 427.223 from here only, that is 427.223, and fly ash this much, water this much, 20 mm down aggregate this much, 10 mm down aggregate this much, sand this much, admixture this much. And if we sum of this all value, it should come above 2400. Since this is concrete only without reinforcement, so we have earlierly studied that for the PCC concrete, the minimum density is 2400 kg per cubic meter. So the density of density, if we add of all the density of each and every constituents, it should come above 2400. In our lab we are casting 6 cubes, three for the 7 days and three for the 28 days. We don't cast the cube for 3 days and 14 days. We only cast for 7 and 28 days. So total is 6 cubes. So for the 6 cube, I have calculated the quantity of every constituent. For that, simply I have multiplied with 0.025. Means here I will show you from where I have taken 0.025. Since we all know the size of the cube mold is 15 by 15 by 15. So if we multiplied this 0.15 into 0.15 into 0.15, it's the volume of 1 cube. But we are casting 6 cube, so we'll multiply by 6. We will we have got 0.020. Sometimes there is some wastage of concrete while calculating the slump value or something like that. So for that wastage, we have, for the safe side, we have taken 0.025. And if we multiply this all value that we have calculated for 1 cubic meter, we will obtain this value. Yeah. So here I have shown you the clear explanation of each and every step. But also, if you have any queries or confusion, you can freely ask me in the comment section. I will try to explain each and every doubt. So for now, thank you for your patience. Uh, now I will upload this Excel sheet in the description section also for your reference, and I will upload this all codes. This code is Nepali code that we are using, and so for the Nepali code also we are taking reference from the IS code only. So IS 256, 10262, IS 383. So this all code I will upload in the description section. So thank you for your support. Please like, subscribe, and share this videos so that among your civil engineers friends, so that they can also learn about the basic concept of the concrete mixed design calculation. Okay.